temple can take us anywhere at any time we want. Just say the magic word.
Abracadabra?
No! Parabola!
Well, I was close.
Arched bridges became popular with the Romans, who used stones in circular and then elliptical arrangements. When steel and concrete took over as building materials, the parabolic arch was determined to be the most efficient structure. As we've seen, a parabola is revealed when a cone is sliced parallel to its slant side. Let's place the parabola onto the Cartesian plane and see how the equation compares with the circle or the ellipse. The simplest parabola has its vertex at the origin and is symmetric about the y-axis. This symmetry is revealed in a table listing some of the points. When x is either 1 or -1, y is 1. When x is 2 or -2, y is 4, and so on. The emerging pattern shows that y is equal to x squared, and this is the core of all parabolic equations. And because the square of something is always positive, the y value is always positive, which is why this parabola opens upward and doesn't extend below the x-axis. A parabola that does open downward is y equals -x squared. This parabola, in effect, is a reflection of y equals x squared. All the y coordinates are now negative. In transformation notation, t maps xy onto x negative y. T is a reflection transformation. As with other figures on the Cartesian plane, a translation can be used to move the original parabola to a different location on the grid. Let's apply a translation to the parabola. T maps xy onto x plus 3y, a slide 3 units to the right. As we've seen with the circle and the ellipse, a plus sign in the translation corresponds to a negative sign somewhere in the equation. We've replaced x with x plus 3 in the translation. So we must replace x squared with x minus 3 squared in the equation. Now let's use a slightly different translation that affects both x and y. It maps xy onto x plus 3, y minus 4, and slides the original parabola to the right 3 units and down 4. Following the opposite sign rule, the equation for the shifted parabola can be determined. We usually write the equation with the y isolated. If we apply a dilation to the parabola, we can get a variety of different shapes without changing the orientation or position. Take, for example, the dilation t, which maps xy onto x 1/3 y. There is another opposite rule that applies to dilations. If we multiply by a factor in the dilation, then we divide by that factor in the equation. In this case, y is multiplied by 1/3 in the dilation. So we must divide y by 1/3 in the equation. isolating y, the new equation becomes y equals 1/3 x squared. And when plotted, looks like this. Sampling some points on the two parabolas, each new y-coordinate is 1/3 of its old value. The y values can be made larger by using a larger factor in front of the x squared, say 2. This results in a parabola that is narrower. There is a general equation for parabolas that have vertical symmetry. The general equation has values like a, h, and k instead of numbers, and we can identify the characteristics of the parabola independently. For example, the value of a controls the shape of the parabola, wider when a is closer to 0, or narrower as it moves away from 0. A also determines which way the parabola opens, upward when a is positive, downward when negative. H represents the x-coordinate of the vertex. As we've seen, a positive h implies that the vertex lies to the right of the origin. A negative h would shift the graph to the left instead. Notice that a plus sign in the brackets indicates that h is, in fact, negative. Finally, the k represents the y-coordinate of the vertex. Anything greater than 0 lies above the x-axis. We can determine an equation for the retractable roof of Sky Dome in Toronto by establishing a set of axes to work with. Let's represent the base level of the roof with the x-axis and have the y-axis run through one of the supports. The roof is essentially a parabola-shaped bridge, which spans about 200 meters. The height of the roof in the center is about 50 meters. Knowing the coordinates of the vertex, h must be 100 and k must be 50. But we must still find the value of a. We also know that the point 200, 0, is on the curve. So if we replace x with 200 and y with 0, a will be the only unknown. A turns out to be very small. In the next program, we'll look at the distinctive shape of the hyperbola.
Hey, Charlie, let's use a retractable roof on our ship.
Yeah, right, Ed. We can put the top down and feel the wind through our hair.